It's my pleasure to introduce Professor Sudarshan Kumar. He's an Institute Chair Professor and Head of Department of Aerospace Engineering. He has a PhD from IIT Bangalore in 2004. He has a very impressive resume. I'll just keep it short in the interest of time. His research areas are in combustion, emissions, fuel, aircrafts, and rocket propulsion. He is a fellow of INAE, fellow of the Combustion Institute, associate fellow of AIAA. Five of his students have received the Best PhD Thesis Awards. He's a prolific in public journal publications. He has over 120 publications with the H index of 36. He has 4 patents.
Thanks, Professor Abhijit Chatterjee. We'll be putting up today a challenge which was envisaged maybe around 50 years ago, which is why combustion even today contributes to around 85% of the energy which is to be used. That I take a liter of fuel and that packs as much as 45 to 50 megajoules. Whereas if you consider a battery, it just doesn't go beyond even 1 megajoules. So if you look at this cartoon, basically it tells that my battery is too heavy to carry. But then combustion based systems can be very light and they can be carried much easily. This is another cartoon. So the application is for defense, so that is why I put a cartoon of a soldier over here, that they have to carry the heavy batteries in the war front, and charging those batteries is another challenge. Like if you look at this figure, that if you look at these batteries after a couple of hours, their voltage starts dropping down, lithium being highest around 10 hours or 12 hours. But you look at the microcombustor, the charging time is perhaps a few seconds. You have to just replace with another can and again it will start working, and you don't feel any pinch in the performance. The densities, energy densities, basically look at, these are the batteries and these are the fuel, like methane or hydrogen, they carry a large amount of energy. So even if we have a system which is operating at much lower efficiencies, even then they would appear to be much better in terms of performance. Another way of looking at it is gravimetric versus the volumetric. Even in that case, this is where the batteries occupy a very large volume. Gaseous, of course, very high gravimetric, and the liquid fuels, of course, are the best. But then at times it becomes a challenge to burn these liquid fuels, because the system's need is like, we need to make a spray out of this liquid fuel and then burn it, and the volume required is much larger. And when we get this heat from the combustion, how do we convert it into electric power? So there are different ways which have been proposed as well as investigated, like micro engines, thermophotovoltaic converters, thermoelectric generators, fuel cells, piezo-based systems, micro gas turbines. So the micro gas turbine was one of the systems which was proposed by MIT way back in 2000, but then it had some of the serious issues. However, then it took up like the combustor as small as 2 to 5 mm. Like 2 mm is kind of a dimension considered. Like if you look at your domestic stove at your home, when you do the cooking over LPG stove, the size of those holes is typically of the order of 2 millimeters. The reason is, when the premixed mixture of fuel and air comes out, the flame cannot enter through that hole, and that acts as a safety device. And that safety device was way back, was designed by Humphrey Davy, the miners, and it was also called as a miner's lamp. So the challenge is that when you get to these dimensions, can we stabilize a flame? So various concepts have been worked around, and this is a summary of some of them. Like this is Swiss roll, which was proposed by Paul Roney in USC, California. Then this is in Tohoku, Japan by Kim et al. And then our group started working on these step combustors, which is over here by one of my earlier master students back in 2010-11. And of course, some other concepts were also there proposed by the researchers. And these are the other concepts like micro gas turbine by Epstein in MIT, and the Shimkuri et al. In Japan. This is I think 2015, 16 and so on. Now in these systems what happens is, like when we go for these thermoelectrics as compared to others, like thermophotovoltaics do give an option, but then the size becomes too large. And the another challenge is the rotating machineries like engines, gas turbines, but then when you make these systems really very small, the friction losses become too large, and hence it again becomes a challenge to design such a system. So the option, this is what we explored, that is thermoelectric based generators. So here what we do is that we take a high temperature source, the heat is transferred to the TEG from the microcombustor, and then to the sink, and part of the heat is converted to the electricity. So if we do the energy analysis, significant amount of heat goes through the heat loss to the surface, heat rejected to the sink, goes as exhaust gases, and some part is converted to electric power. And then the next challenge was, like, can we get these thermoelectric modules of the size what we want? So although we were able to design combustors in the laboratory as small as 2 to 5 watts, which were something like 1/10 of a candle flame. No, sorry, not candle flame, a matchstick flame. So matchstick flame itself is difficult to stabilize, but then 1/10 of that size flame we stabilized, and it was working continuously for hours together. And taking that flame, and then what we found is that we cannot get the module smaller than this 1 inch by 1 inch. So then we did certain modifications and started working around with this, and started developing these micro power generators, putting these modules around these microcombustors, working on the different strategies of maximization of the thermal management, then maximum power point tracking, and combustion stability. So these are some of the examples over here. Like if I show you this, so here the central portion is the microcombustor. These are the modules, one on the top, one at the bottom, and these are the sinks through which water is circulated to take out as much heat as possible. And the size of this is very close to what a typical battery we get in the market, which gives us roughly around 3 watts of power. And this system can give around 4.5 watts of power. And now we started packing around this microcombustor. As you can see over here, initially what we did was we put up a multi-step combustor over here where dimensions vary from 2 millimeters to 3, 4 and 6, and the combustion products go out through this way. So the path is chosen to ensure that maximum amount of heat is recirculated, and then this heat is transferred to the modules. And then we went on to fit in 2 combustors within this same dimension, but here now the way was different. The combustors were on the outer side, and then the combustion products were going through this inner way. And this front hole is for the ignition of the mixture by opening this part. Looking at the typical performance, we were able to achieve the thermal power inputs. This is red one is for single and green one is for the dual system. And these were the delta T, that is the temperature difference across the modules, and the converter efficiencies touching roughly around 5% overall. And then we also looked at the different ways of that instead of water heat sinks can we make use of this air or the typical aluminum sinks for the with cooling fins and the cooling fan put together. And these investigations showed that this typical size is something like this. And the performance was like, when we use water, we get very good performance. When we use only the fins but no fan, then this green line is shown over here. And this blue line is when you use fan for the cooling of the fins, we get a much improved performance. And the different figures just show that the overall efficiency with water touches 5%, but with this fin and fan, it touches roughly 2.5%. And if you look at how much of the power is consumed by the auxiliaries. So when we use only fins, it's roughly 0.3 watt which is generated. Fin fan configuration, roughly 0.3 watt power is used by the accessories. When you go for water, it is 0.22 watt of the power is used by the accessories, means pushing in the water through the cooling channels of the sink. And then we also developed a mobile charging using this generator. So this is the whole system in the test rig, and then the power output from this board is connected to the mobile device for charging. And it shows that the system is getting charged. And then we also explored at the other options of self-aspirating microcombustors, where currently Dr. Asad is working on this, and he has not only worked with gaseous fuels but also liquid fuels, and self-aspirating microcombustors are currently being developed in the lab. And this is one of the demo units which we built and displayed in the DEF Expo a couple of years ago before the lockdown in Delhi. And this system is roughly of the size of the mobile. And we also developed another unit which was slightly of, you can say, instead of micro, a mesoscale. So this system was 2.5 inches by 2.5 inches. And this system was able to develop something like 20 watt of electric power with conversion efficiency of 3.1%. And these 4 bulbs were lit using the power output from the system. And if we compare our work to the what is going on across the world, so this picture shows that the combustion efficiency, one is for air cooling based system, other one is for water cooling system. So among the air cooling, we achieved the best of the conversion efficiencies across the world. In water cooling also, the topmost points all belong to our laboratory, thanks to all students who have worked over the years on this technology. And with this, I would like to finish my talk, and acknowledgement to all the students who have worked in the lab over last 15 years or so. So any questions? Yeah, welcome. Thank you.